Okay, scalars and vectors. Definitely something that you can't skip because it comes up all the time. Even if you're higher set, top set, and you're really confident with all things physics, it's important to be able to tell the difference between a scalar and a vector quantity. Scalars are things that have a magnitude, which means size only, and a vector is something with both magnitude and direction. Now, it's something to think about. 2 degrees Celsius can go up to 3 degrees Celsius, but it's only the number that's increasing. It's only the magnitude that's increasing. Temperature can't go right and it can't go north. So it doesn't count as a vector quantity. So just be careful when you think about it. Is it the number that's increasing, or is it the quantity, something that we can measure that is increasing, changing direction? Um, when we think about the importance, why is it important that we can tell the difference between vectors and scalars? Well, if object A collides with object B and they're going in the same direction, then we need to know that the speeds are, if they're going in the same direction or if they're going in opposite directions. Because if they're going in the same direction, then the effect will be a lot different to if they were going in opposite directions. Could not tell you why I wrote that as a backwards B, but there you go. I don't know. It is what it is. So if they're going in the same direction, then it's going to be a much less of a collision. If they're going in opposite directions, it's going to be a much greater a collision. So sometimes it's just important that we know if something is a scalar or a vector. Here are some examples. Now, for a couple of the definitions, it'll be quite tricky. Displacement is a straight line distance between point A and point B. This is not a straight line, but I would like you to pretend that it is. All forces are vectors. And remembering that acceleration is the change in velocity divided by the time taken, then it's not the change in speed, it's the change in velocity. And momentum, higher tier only, momentum mass times velocity. Here's some definitions for you to read if you'd like to just pause. Okay. Here's some questions. And answers. Okay. Some definitions for speed and velocity. Speed is the rate of change of distance. Velocity is the rate of change of distance, but with a specific direction. Okay, some example speed calculations, what they might look like. Another. Velocity calculations. Now, average speed is the speed of an object over an entire journey. So if we start off at A and we want to go to B, and in this little block here, we're going 2 meters per second, and then this little block here, we're going 1 meter per second, and then this little block here, we go 6 meters per second, then the average speed would be the total time taken between A and B, and the total distance between A and B. Instantaneous speed is the speed of an object at a given moment in time. So if I wanted to just look at here, let's say, for example, that's 4 seconds or whatever. At 4 seconds, the instantaneous speed here would be 6 meters per second. Here at 1.7 seconds, the instantaneous speed is 1 meter per second. Now, distance time graphs. Again, people think they're quite simple, but they can be a little bit tricky, especially if you miss what the axis is saying. So this is a distance time graph. Distance time graph, not to be confused with the velocity time graph. But the different gradients or steepnesses of the lines show different motions of the object. So looking at this green line here, starts off at 0 and it covers like 1, 2, 1, 2, 3, 4, 5, 6, 7. It covers 7 units of distance in about 3 units of time. But the red line only covers 2.5 units of distance in 3 units of time. So let's say it was 7 meters over 3 seconds and 2.5 meters over 3 seconds. This is going to have a much greater average speed than the red line. A line with no gradient shows a stationary object because the distance is not increasing as time is increasing, which means the object isn't moving. Here's a go of having a go of that. Your answers, and again, we can find the acceleration of an object if we've got the change in velocity. Now, it's difficult to do that with a distance time graph. It's much easier with a velocity time graph. But acceleration is when objects change speed or change direction or change both speed and direction. And we'll come on to this later on when we're looking at centripetal force. Acceleration is the rate of change of velocity. And since velocity is a vector, so is acceleration. So acceleration is also a vector. A is equal to v minus u over t. If you think about the alphabet, L, O, P, Q, R, S, T, U, V, W, X, Y, Z. V comes after u in the alphabet. So v is the second speed and u is the first speed. So u is the starting speed, v is the end velocity, u is the initial velocity, v is the final velocity. It's just something to help you remember which number to plug where when you're doing your calculations. Here's the answer. Because acceleration is a vector, the direction is important. So an object can have negative acceleration, and that can mean that it's either slowing down, so the magnitude is decreasing, or it could be increasing speed in the opposite direction. Positive and negative motion just means if I have an object that is going this direction or that direction, minus 2 meters per second and plus 2 meters per second, now it's the same rate of change of distance, but in different directions. If the car is moving along a straight motorway at 70 miles per hour and then has a negative acceleration, it means the car is slowing down. But if the positive direction is chosen to be upwards when a ball is dropped, so here's my ball. If I say that this is now my positive direction, when the ball drops, it will accelerate at minus 9.8 meters per second, just because it's going the opposite direction. And this is only if it's on Earth. This equation is in the back of your paper, your exam paper, when you're doing it. V squared minus u squared equals 2 times a times x. The x there is distance or displacement. It's one that pops up frequently, and people try to use this equation to try and find the answer when they actually have to use the distance one. So if there's an acceleration, a change in velocity, and they're asking you to find distance, or if they give you distance and a change in velocity and they're asking you to find acceleration, this is the equation that we need to use. Another example of what that kind of question might look like. What's important to look at so one of the things that might happen is that when you're given an object that's at rest, you'll think, well, I've only got one velocity here. They've given me a distance, they've given me the acceleration, they want to find a velocity, they want me to find the final velocity. Where's my initial velocity? An object that isn't moving, has got a speed of 0 meters per second. Velocity time graphs give a lot more information. You're able to find the acceleration and the distance traveled by the object. The line shapes look the same, but they mean different things. So on the y-axis here, we have velocity in meters per second. Velocity in meters per second. Now, remembering that acceleration is the change in velocity divided by time taken, we can see that we can find that change in velocity and the time taken for that change when we put intercepts into the graph. The acceleration of this object goes from 0 to 20, so that's 20 meters per second, in 20 seconds, meaning my acceleration is 1 meter per second squared. When my line has got no gradient, then it is not stationary, it is at a steady speed. This object went 20 meters per second for 20 seconds. Something else, it's not for 40 seconds, it's for 20 seconds. So this chunk of the graph, this section of the graph, started at 20 seconds, ended at 40 seconds, meaning that if we're trying to find the acceleration of the object here, 0 meters per second squared, it's because we have the there's no change the time is between those 2 points. You can find the velocity from reading off the axes in the graph. So if I asked you what velocity was this object going at section B, it would be 20 meters per second. You can find the acceleration from the gradient. So this is 20, this is 0, this is 10. Delta V divided by T would be 20 divided by 10 would be 2 meters per second squared. So I can find my acceleration at this point. You can find the distance traveled, the area under the graph. The area under the graph will only ever be two shapes. One is a triangle and the other is the rectangular type shapes that we can get, maybe sometimes a square. If I want to find the area under the line, if I want to find the distance traveled, pardon me, I find the area. For a triangle, it's 1/2 the base times the height, and for a rectangle, it's the base times the height. So we can there'll be some videos underneath in the comments section below. I'd like you to watch those. Any questions about them, or if you'd like to have a look at any of the kit, just ask myself or any of your physics teachers, and we'll help you out with them. And we'll show you the different things. Stopwatch, light gauge, ticker timer. Don't really use these anymore. Might get a question on it, so there's a video down in those comments that you can watch as well. But something that often comes up, why is a stopwatch not as good as something like a light gauge? Well, it's because stopwatches require a reaction time in the person. So if you are measuring something with a very small, if there's a small gap between the different things that you were timing, I don't know, so a trolley is coming at you very, very fast and you've got 2 points that are very close together. If you're trying to time something in there and it takes anything less than 2 or 3 seconds, then there's no point using a stopwatch because your reaction time actually won't be quick enough to time that thing from happening. Here's some typical speeds that you need to remember. I'm also just going to pop in here for the sake of it, 300 million meters per second, which is light. Terminal velocity is this idea that there's a certain speed that you can get to when you're falling due to gravity, and after that speed, you can't accelerate anymore. You cannot be increasing in your velocity at all. And the reason for that is that when someone jumps out of a plane, it's the weight that is bringing that person down towards the ground. And at first, there'll be very little air resistance because there'll be a very small velocity. And the greater the velocity, the greater the air resistance, because the more air particles the object will be interacting with. Over time, though, after not actually that much time either, the forces will be balanced. So the force of weight and the force of air resistance will be balanced, meaning that there can't be any more acceleration. When we get to this terminal velocity, terminal just means the end velocity, you can't actually speed up anymore. Fun fact, if you dropped a squirrel from outer space, it would die of starvation and not die of impact hitting the ground. Squirrels can survive a fall from their terminal velocity. It doesn't matter how high they fall from, they will never ever be squished because the speed at which they will reach at their terminal velocity is not enough to cause them damage. But, don't use that as an excuse for throwing squirrels around places. Have a read of this. Pause it if you haven't already. And something to remember, the acceleration due to gravity is 10 meters per second squared unless you're told otherwise. Here's a picture of those forces we were talking about. At first, there's no air resistance whatsoever because we've just jumped out the plane. Then there's a small amount of air resistance as the velocity of the diver increases. And finally, we get these balanced forces, meaning there can't be any acceleration. Here's some estimates of magnitudes for everyday accelerations, and we'll give that 10 seconds. And some questions. And the answers? Alrighty then. So higher tier only this, we're talking about circular motion. So in a perfectly circular orbit, an object will travel at constant speed to maintain its orbital distance. However, gravity is constantly changing the direction of the object. As velocity depends on speed and direction, the velocity is constantly changing even though the speed remains the same. Now, this doesn't just happen. This circular motion doesn't just happen when we're talking about the orbits of an object. Also, anything that swills around the place, like fairground rides, moons and satellites. We can also talk about maybe a car that's driving around in a circle, someone on a swing. Because the object travels in a circular motion, it's prevented from moving off in a straight line by this thing called a centripetal force. So here is my object. It is moving around in a circle. As it's moving around in a circle, there is a force of attraction towards the center. Now, that force of attraction could be tension on a string. It could be friction if it is between the wheels of a car and a roundabout. Or it could be gravity if it is something that is orbiting a planet. This object wants to move in a straight line. That is the velocity of this object at this moment in time. Let's say it's 2 meters per second and it is going left. However, the force that is pulling it towards the center causes its motion to actually be diagonal. The force that's pulling this object towards the center is called the centripetal force. And we say that this object is accelerating. Because even though the velocity can stay the same, let's say it's 2 meters per second here and 2 meters per second here, the velocity is the same, but the direction is changing. And because acceleration is a vector, meaning it has to have a magnitude and a direction, we say that an object traveling in this circular motion is accelerating. If I was to cut the string, then my object would carry on, in its original direction. So I don't know, slingshots or whatever you like. And the link for this video will be down in the comments section. Now, inertia can be a little bit difficult for people because we use the same units that we use for mass when we're discussing inertia. Inertia is a property of matter. It's a measure of how difficult it is to change the velocity of an object, including if it's from rest. It's the ratio of force over acceleration. So the ratio of force over acceleration can be described if we think about our equation F equals A times m. Let me rearrange that for m, and we find out, and we see that mass is equal to the force over the acceleration. So inertia can sometimes be referred to as inertial mass. The mass is a measure of how much inertia an object has. The more mass an object has, the harder it is to get that object to change its motion. To find out which of the two objects has the most inertia, apply an equal force to both of them. When they're at rest, the one with the greatest acceleration has the lowest inertia. Now, Newton's third law of motion. Whenever two objects interact, the forces they exert on each other are equal in size and opposite in direction. This is not the same as resultant force. Okay? Newton's third law of motion requires two objects exerting two forces on each other. Resultant force is the sum of all the forces acting on one object. An example of this is that a book on a table will be pulled down by Earth by its weight. Momentum is a vector quantity. Moving objects have momentum. It's the tendency of an object to keep moving in the same direction. It's difficult to change the direction of movement of an object that has a lot of momentum. The momentum of an object depends on its mass and its velocity. So momentum is this idea that if I've got a large thing moving in a particular direction, it's going to be hard to make that thing change its direction. If I've got a fast thing moving in a particular direction, it's going to be hard to change that thing's particular direction. If something has no momentum, it means it's either not moving or has no mass. And no mass doesn't happen at GCSE, so we'll just say that whenever something isn't moving, it means that its velocity is equal to, if we ever say something has no momentum, we say that the velocity is 0 meters per second. The momentum is a conserved quantity. The momentum of a system remains the same before and after an event. All that means is, let's say I've got object A about to crash into object B, and there are 2 bits of momentum here in this scenario. After A crashes into B, this second scenario, there will still be 2 bits of momentum afterwards. Now, the units for that, kilogram meters per second, just means that the total amount of momentum before a collision is equal to the total amount of momentum after a collision. In an explosion, the momentum of the system is also conserved because the amount of momentum before a collision or is equal to the amount of momentum after a collision. Now, it might seem strange because everything is stationary to begin with. So we've got two people here now who are about to push against each other. We can call that an explosion. Right now, they haven't pushed anywhere, so the amount of momentum is 0 kilogram meters per second. They're going to push off each other, and they're going to start going in different directions. Let's say they go back at 1 meter per second, and she goes back at minus 1 meter per second. Why have I said minus 1 meter per second? Well, because it's going in a different direction. After the explosion, parts are moving to the left and to the right, and they cancel, because velocity is a vector and it depends on direction. So the total momentum before these two pushed each other, this is V4, is 0 kilogram meters per second because they're not moving. Afterwards, They are both 50 kilograms in this example. She is going 1 meter per second in that direction, and he is going minus 1 meter per second in that direction, meaning that the amount of momentum the momentum of each of these will be the velocity times the mass. That will equal 50 kilogram meters per second and minus 50 kilogram meters per second. And when I add these two together, I get 0 kilogram meters per second. So the total momentum before is equal to the total momentum afterwards. Newton's second law, changes can be used to describe changes in momentum as well. Now, we know this equation, F equals m times a, and we know this equation, A is equal to v minus u divided by t. Combining these two equations, what that means is putting this a in here gives me F equals m times a, but putting the v minus u divided by t into here, which you can do because a is equal to a, gives me this equation. The force is equal to the change in momentum divided by time taken. You can also see this as delta p divided by t. You can use this to describe the forces that are. You can use this to describe the amount of force that's in a collision or in a change of momentum, or it can also be used to describe why we need things like seatbelts, airbags, and crumple zones. If I want to reduce the amount of force during a collision, I have to increase the amount of time needed for that change in momentum to occur. If I increase this denominator, then it means that the total amount of force will decrease too. Airbags work by increasing the time of impact. So the person's head would normally just smack onto the steering wheel. But if there's an airbag in a way, then it takes longer for the head to smack on that steering wheel. And even a small increase in time can lead to a huge reduction in force. And we've got some maths that we can look through. There'll be a link down there for that as well in the comments. Seatbelts also increase the time taken to stop. They give a little bit before they lock in. They don't lock in straight away. There's a little bit of time before that lock occurs, which means that the amount of time is increased for that change in momentum to occur. Here's some questions. And your answers? Right, thank you very much for listening. Any questions, let me know. And remember, any mistakes, tell me, and you get achievement points. Ooh.